Oh, hey, I didn't see you there. Welcome to Zach's transport lesson. Today we're going to be talking about the modern marvel of technology that is the gas-powered water heater, which allows me to enjoy such luxuries as this hot, nice shower. We're going to be taking a closer look into the heat transfer that occurs in this everyday appliance. As you can see, the water heater is made up of three major components. The first is the combustion site. Here, air from the surroundings is drawn in and combusts with natural gas to function as the heat source for the unit. Next, we have the combustion gas flue. Heated carbon dioxide and water vapor produced through the combustion reaction rise through this flue and transfer heat. As you might imagine, the flue gets hottest at the bottom of the tank, near the combustion site. As the gases move further up, they lose more and more of their thermal energy to the flue, until they emerge through the flue gas vent at a much lower temperature than they started. Heat transfer is aided by the spiraling fin inside, which increases the surface area for heat transfer and makes the process more efficient. We'll get more into this in just a bit. Finally, we have the hot water tank itself. This is where the main water inlets and outlets are located and where the majority of water flow occurs. Unheated water enters the tank through the cool water inlet and is guided to the bottom of the tank. As the cold water interacts with the hot gas combustion flue, it begins to heat up. As the water heats up, its density decreases, causing it to rise towards the top of the tank. As it rises, it is continually heated by the flue gas column. Once the water has reached the top of the tank, it has been fully heated and is ready to steam up your shower. This heat transfer process is actually similar to what you might see in a co-current heat exchanger, as is shown here. Both the hot and the cold stream are traveling in the same direction. This type of heat exchange doesn't always make for the most efficient system, but works well for a hot water heater because no pump is needed to make the flow of water move. Density gradients and gravity take care of that for you. Alright, so let's go back and consider that fin in the flue shaft and its usefulness to the system. We generally do this by comparing the ratio of heat transfer with the fin compared to the heat transfer that occurs without the fin. Fin performance is based on a variety of factors, including length, volume, thermal conductivity of the material used in the fin, and the thermal properties of the surrounding fluid. In our case, this is going to be the thermal properties of carbon dioxide and water created by the combustion reaction. We can use equations derived specifically for different situations of fins to calculate the heat transfer through a fin. For more about these equations, please refer to the supplementary document to this video. So, we will define efficiency as the Q of our fin divided by the Q that would occur without the fin. Getting more mathematically into this, that would be our Q of the fin as calculated by those equations I mentioned earlier, divided by the heat transfer coefficient for our fluid times the area of the base, and that would be without the fin at all, multiplied by our theta of the base, and we will define theta as the temperature of the, we will define it as the temperature of the fluid minus the temperature of the base of the fin. So using this equation, we can determine whether the heat transfer through the fin is being aided or impeded by the presence of the fin. In the situation of a hot water heater, as long as the heater designers did their homework and made the fin out of a thermally conductive material, we would see the fin effectiveness as something greater than 1, or that it's aiding the system. So, just to review how a natural gas water heater works. A combustion creates gases that rise through our flue. These gases transfer heat through the fins that we talked about which then transfers to our fluid. The heat transferred to the cold fluid causes a density change in the fluid, and it rises through the tank. This creates a pseudo-co-current heat exchanger effect. Finally, the heated water exits the tank to your shower. I hope you learned something about this commonplace household appliance that doesn't get all the credit it deserves, the hot water heater. Enjoy the rest of your day.
Okay, this is the Reynolds number song. Now, Sir Osborne Reynolds was a man of yore who liked to play with cymbals that you might think a bore. But he figured out a problem and acquired some fame, and now the Reynolds number bears his name. You take a D times a B and a rho by mu, put them all together with a little bit of glue. Then you've got a number that'll see you through. It'll tell you what the fluid's going to do.